Welcome back, friends. So we started looking at unitary groups, and the entire question, if you remember, came arouse about the Dirac equation and how does it transform under Lorentz transformations. Essentially, that was the basic idea. Now for that we started looking at group theory, basic group theory. So looking at a set of groups which are called Lie groups, which are continuous groups, and so we started looking at writing them in various forms. Essentially we started these continuous groups. The orthogonal groups, we have seen that there are something called generators, which are generators of infinitesimal rotation. So we started with rotation group actually. Then we started going with unitary groups essentially, okay, and in between we started also talked about the boost, Lorentz boost, and the Lorentz boost do not form a group because two boosts will give you a rotation. I will come back to that in some point essentially, okay. Okay, we will come back to that in some point, but now we are good looking at rotations in complex vector spaces. So we are looking at rotations in complex vector spaces, which are essentially for, we started looking at SU2. So we are looking at SU2, and SU2 we have started looking at we will look into more detail for SU2. So SU2, how many generators it has, what does it do, what are the generators of SU2. These are the kind of questions we will be asking. I will continue today, and then we will proceed further to the Lorentz group and its transformations and everything essentially. So okay, so what we were looking at is this particular aspect, complex vector spaces. So we started looking at complex vector spaces and rotations in complex vector spaces. So if we have a general complex vector Z, which contains Z1 and Z2, and there is a rotation U, okay, which takes this complex vector to Z1 prime and Z2 prime vector, which is also called Z prime, okay. If this is the case, then the demand is that the norm of the vector should remain invariant under this transformation. This transformation is so let us say it is a rotational transformation. Under this transformation, okay, under this transformation the norm, and this will turn out, this will put constraints on this particular matrix U, and this matrix turns out to be unitary, meaning U dagger U should be equivalent to 1. We can simply see it from this relation that Z prime dagger Z prime should be equivalent to Z dagger U dagger U Z, that should be equivalent to Z dagger Z. So this means U dagger U should be equivalent to 1. Now imposing these conditions on it, essentially we see that a typical unitary matrix has and the number of entries of a typical unitary matrix, free parameters of a unitary matrix are 4, because if you start with a unitary matrix of 2 by 2 dimensions, it has 8 real entries. So 8 real parameters, because each parameter has a real part and an imaginary part, okay. And so if you impose the condition of unitarity, which is essentially U dagger is equal to 1, on the right hand side all the imaginary parts are 0. So this will imply that there are 4 conditions on these 8 real parameters, and this will give you 4 parameters which you can define a unitary element, essentially an element of a unitary group essentially. So and a general UN a UN unitary group would have n square number of elements, essentially n square number of elements, okay. Now then we made a special case essentially that in addition to being unitary, the determinant of the matrix should also equal to +1, not even anything, okay. It should be equivalent to +1, that is called special unitary, okay. if the determinant of the matrix should also be plus 1, so that will end up being a special unitary matrix. So those are called SUN groups, essentially SUN groups. So this gives you an additional condition in SO3 or O3 orthogonal groups. This one doesn't give you an additional condition, but for unitary groups it gives you an additional condition. So this condition would be an additional condition. So the number of elements of SUN group will be n square minus 1. So the number of free elements parameters okay, n square minus 1. So that is equal to so that will be for SU2 group. So now let us look at SU2 group with 2 dimensions a bit more carefully. SU2 group has 2 square minus 1. So number of free parameters are 3. So this can be are 3 parameters essentially, but they are in complex space, essentially on complex vector spaces. So that means there are 3 generators, there are 3 rotations, there are okay in complex vector space of 2 dimensions. Of dimension 2, and that also signifies that there are three generators associated with the 3 parameters. Associated with the parameter. So just like in orthogonal groups, we have 3 rotations x, y, y, z, z, x. Here also we can think in terms of 3, but this is only a 2-dimensional space essentially. This is a 2-dimensional space. In this, what could be the generators? The generators turn out to be essentially they are very well known matrices which we have been associated with all the times. The generators of SU2 are sigma I, which is nothing but sigma x, sigma y and sigma z. Now this is nothing but the Pauli matrices. The reason is because in 2-dimensional matrices the number of linearly independent Hermitian matrices is only 3. Okay, the number of linearly independent Hermitian matrices is only 3, and there is only one vector space which it can span with the sigma matrices, and the sigma matrices are the most linearly independent set essentially. They form a complete set. Okay, and okay, you can also start deriving these things like what we did. We start with there could be 3 parameters and you can assume them to be rotations, but this will be rotations in 2-dimensional complex vector space. Okay, so you know that this is sigma x 0 1 1 0. This looks like some flip, it's almost like a flip essentially. Sigma y 0 minus I 0, this is on the imaginary plane, and then sigma z which is 1 which is the diagonal generator, this is the diagonal generator. So, there are 3 parameters, and you can show that these are the 3 generators possible, and there are theorems which tells you that in 2 dimensions the number of linearly independent Hermitian matrices are only 3. So, this we have seen also when we are writing uh, the Dirac algebra alpha and beta matrices essentially, and you show that we can use the conditions, similar conditions, essentially traceless Hermitian matrices and everything. Why these should be generators should be Hermitian? The generator should be Hermitian because you can express the SU2 element, any SU2 element, okay, any SU2 element. So, let us take an element of SU2, let G belong to SU2, okay, let G belongs to SU2, then G can be written in terms of e power I theta bar dot sigma bar essentially. Sometimes there is a connotation of factor 2 here essentially, which is completely in your hands. I think sometimes there is a factor 2. Okay. So, this is the reason, because you are having a G is a unitary matrix theta bar is equal to theta x, theta y, theta z, and sigma bar is equal to sigma x, sigma y, sigma z. Okay. Now, so now you see that okay, there is this well known theorem in quantum mechanics also that any unitary matrix U is equal to e power I h, where h is Hermitian. So, the exponential of a Hermitian matrix ends up being unitary matrix, and now you can show it that you can assume that U dagger U is equal to 1, and then you can show that from that you can get h is equal to h dagger. Similarly, if you assume h is equal to h dagger, and you can show that U dagger is equal to 1 essentially. So, this is a theorem which pretend. So, you have unitary matrices which are given in this particular fashion, and these are your sigma matrices essentially for the first. Okay, these are your sigma matrices. So, the Pauli matrices which are associated with spin in quantum mechanics appear in the as generators of SU2, as generators of SU2. Okay. Pauli matrices, this is an important point essentially. Associated with spin half in quantum mechanics. Pauli matrices in quantum mechanics appear as generators of SU2. So, that means SU2 is also a generator of angular momentum. Angular momentum. Which is not surprising, but anyway, this is what we learn already in your quantum mechanics essentially. We know this is the case essentially in quantum mechanics. So, also the generators of angular momentum. Now, so SU2 what we have seen is that it is if you have on a complex vector space, it appears, okay. So, U is equal to so e power I theta bar dot sigma bar, and theta is a non-abelian group, y because sigma I sigma x sigma y is equal to I sigma x y z sigma z. Okay. So, there is this non commutation relation satisfied by the three generators of the group. So, it is a non-abelian group. Okay. This is the group of, okay. So, this is the group in 2 dimensions of sigma matrices essentially of unitary matrices. Good. Now, what are and it keeps norms and everything of C. Now, what we are looking at is there are a couple of things we should mention here that. So, we are looking at unitary groups essentially. So, but what we are looking at, what we need to know a little bit more about is something called the concept of representation. Okay. Now, there is a given a group, say for example, given a group, say for example, some group you take essentially that okay. So, some group so let us take rotation in 2 dimensions, say for example rotation in 2 dimensions cos theta sin theta minus sin theta cos theta. This is x prime y prime. So, this is a rotation under 2 dimensions which keeps the length of the vector x square plus y square is equal to x prime square plus y prime square. Now, instead of x and y, you can think of some other vector space essentially for the same rotation group. Now, the same rotations can be mimicked in some other vector space, let us say some other vector space made up of psi of x y. Let it have components psi of x y, psi of psi 2 of x y, and this is some vector space. In this vector space, the rotations group forms a representation, it will not appear as cos theta sin theta or something essentially, it forms a representation. So, if you call this matrix as some u of theta, so this will be some r of u of theta. So, this full matrix will be some r of u of theta, okay, and this should be equivalent to psi 1 prime x y, psi 2 prime x prime. Okay. So, what is this? So, this is also okay. This matrix is called a representation of the rotation group. It forms a representation of the rotation group. Now, this can have, you can take, you are taking complex vector spaces, that's the representation will be different essentially. You can take any kind of vector space you want essentially, you can take a real vector space, you can take 3-dimensional vector space like we have seen essentially. A 2-dimensional thing will only appear as a 2-dimensional rotations in 2 dimensions. You can take a 3-dimensional vector space, you can take a complex vector space, you can take any other vector space. As long as the group multiplication law is satisfied by the representation, it forms a representation of any group essentially. It is not just, I had just given an example of a rotation group. So if the group multiplication law of any group is, say for example, g theta and g of theta prime is equivalent to g of theta plus theta prime, okay. Okay, if this is the group multiplication law, okay, maybe let me put it in more accurate terms, essentially that okay, g of theta, I am writing in terms of rotation angles essentially. Now there could be a vector space in which there could be an r of theta, there could be an r prime of r of theta prime, which could leave you to theta plus theta prime, which follows exactly the same group multiplication law, exactly mimics the group multiplication law okay, exactly mimics the group multiplication law on a different vector space. In that case both R and the vector space, say psi of theta, psi 1 of theta or whatever it is, are called representations of the original group of the representations of the group G. Say for example G belongs to G, okay, they are called the representations of the group. So you are thinking of a different vector space essentially, okay. Now okay, so depending upon, so okay, let me put it, let us come back to explain it more, let us come back to this question of rotation essentially. Rotations, we were discussing rotations. A rotation in a complex vector space will look different. It could be because a rotation in 2-dimensional vector space will look different. A rotation correspondingly in a complex vector space will look different. A look this, but it is the same rotation. The transformation is just one single rotation in 2 dimensions. Okay, let us just take this transformation in 2 dimensions. So this is your operator, and this operator will have representations in different vector spaces which are different, okay. Otherwise let us put it in languages, essentially in another language, so that it makes understandable, that in say, and the analogy with quantum mechanics. The operator, the abstract operator O, will have a representation in the complex vector space psi as O is equal to psi prime, okay, psi, and this will be some matrix essentially. So some matrix essentially as psi I, okay. So each element would be so the O would be essentially, this is your matrix, okay, O, and it has a representation, this is a representation in the vector space of psi, okay. So this each element O11, this will be O11, O12, O13 and so on, so ONN, okay. So because we are much more maybe familiar with quantum mechanics, so I am just taking an analogy with quantum mechanics essentially. O11. Now if you change the vector space, if you change the vector space, instead of you take a vector space which is chi, okay, if you take a vector space chi, so for example chi, okay, chi I, chi j, the operator will have elements which are different, essentially this will be in the vector space. So this is a different representation for the same operator. For the same operator, this operator is always abstract, it is same, it means something, say for some translations or something essentially, but in different vector spaces, say here it will be again chi 11, 11 O12 O13 n, okay, so it will go on essentially ONN essentially, okay, but this is evaluated in the vector space chi, okay, in the vector space chi essentially. So this is a completely different representation. So you can have, okay, so this is a completely different representation, okay. So the representation is, and now instead of an operator, now you just think that this operator is nothing but a group element. Why do you say that? How do you make, actually how can you make such a statement essentially, okay, this is exactly, in fact this is mathematically completely correct actually what I am doing. I am actually, I just told you that it is an analogy, but there is something called a Wigner's theorem, which tells you that most of the, okay, most of the operators essentially which are most of the physical observables are represented by unitary or anti-unitary and operators on Hilbert space. Okay, most of the physical, actually this is all the all let me put all essentially, okay, all of the physical observables are represented by or physical symmetry transformations essentially, and most of the physical observables are related to a symmetry transformation. Or most of the symmetry observables, let me not put all essentially, there could be other thing, but anyway, come from a symmetry transformation. Now what I said, actually Wigner's theorem is associated with symmetry transformations, all the most of the symmetry transformations are represented as unitary anti-unitary operators on the Hilbert space, but in physics most of them, I actually twisted it because most of the physical observables in physics come as symmetry transformations essentially. So what are the symmetry transformations? Say for example, okay, the symmetry transformation of translations leads to some conserved quantity, okay, because most of the physical observables are conserved quantities, okay, so which will lead you to something called Noether's theorem. The conserved quantity is linear momentum, okay, which is a physical observable. Momentum is observable essentially. And then if we have rotations, this gives me angular momentum, time translations, energy conservation. Energy is a conserved quantity. So these are all your conserved quantities. So these conserved quantities are all your, most of the conserved quantities are your physical observables. Putting everything together, you notice that all the physical observables in quantum mechanical or in Hilbert spaces are essentially your represented by unitary operators, are represented by unitary operators essentially. Okay. So that the unitary operators are unitary matrices essentially, or they correspond to some physical observables, and they are operators on Hilbert space. They are unitary operators on Hilbert space. So at the end of the day, what I am trying to say is that, so we are talking about representations in so the representations in group theory have a one-to-one correspondence to the representations which we know in quantum mechanics essentially, representations of operators. Okay. So the unitary group representations will correspond to some rotation groups, rotations in n-dimensional Hilbert space essentially, which is a physical observable, which will corresponds to some unitary operators on the Hilbert space, and the representations are different for different vector spaces essentially which we consider. So the idea that a unitary group element has different representations under different vector spaces is very similar to a unitary operator on having different representations in different Hilbert spaces essentially. Okay, good. So we will continue further from here. So I will stop here right now and I will continue on this. Okay, and keep thinking about unitary operators and what is the connection between the Dirac equation and this essentially. Okay, okay. Thank you very much.